Have you ever pondered how everything around us, the stars, galaxies, and even we, came into existence? This question has fascinated humanity for centuries, and the most accepted explanation we have come up with is the Big Bang theory. Picture this: around 13.8 billion years ago, our universe was born in a state of unimaginable heat and density. Everything that we know and don't know was compressed into a tiny point of energy, waiting to explode. In this early stage, the universe was a hot, dense plasma of photons, electrons, and baryons. These particles were all buzzing around in a state of thermal equilibrium, too hot and energetic to form stable atoms. But as the universe began to expand, it also began to cool. And around 300,000 years after the Big Bang, the universe reached a critical temperature of about 3,000 degrees Kelvin. This marked an epoch known as recombination, a time when the universe cooled enough for protons and electrons to come together and form neutral hydrogen atoms. This formation of atoms had a profound effect on photons, the particles of light. Prior to this moment, these photons were constantly interacting with charged particles, but with the formation of neutral atoms, the photons were set free. They decoupled from the matter, no longer interacting with the electrons and baryons. These decoupled photons, once confined to a dense plasma, were now free to travel across the universe. As they journeyed through the cosmos, they continued to cool down and lose energy. And today, billions of years later, we observe these ancient photons as a faint glow that fills the universe. This glow is not in the visible spectrum, but in the microwave range, hence its name, the cosmic microwave background radiation. These photons set forth on their cosmic journey, cooling down over billions of years, and what we observe today is the cosmic microwave background radiation. This relic of the Big Bang provides us with a snapshot of the universe at a very early age, offering us clues about the origins and evolution of everything we see around us today. Sometimes the most profound discoveries are completely accidental, just as it happened with the CMB. In the early 60s, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Laboratories. Their project involved a radio telescope, and they were trying to eliminate a persistent low-level noise signal that kept interfering with their work. They tried everything they could think of, from removing pigeon droppings in the antenna to accounting for the radiation from our own Milky Way galaxy. But the stubborn noise remained, a soft hum in the background that simply wouldn't go away. Meanwhile, a few hundred miles away at Princeton University, a group of physicists were on the hunt for the exact thing that Penzias and Wilson were trying to get rid of. Led by Robert Dicker, the team, which included P. James Peebles and David Wilkinson, were working on theoretical predictions of the CMB, a radiation that should fill the universe if the Big Bang theory was correct. While Penzias and Wilson were trying to silence the mysterious hum, Dicker and his team were preparing to search for it. Through a mutual contact, the two groups became aware of each other's work. The noise Penzias and Wilson were trying to eliminate was, in fact, the very signal Dicker's team was hoping to discover. The stubborn noise that had been troubling Penzias and Wilson was the CMB, a residual radiation from the Big Bang. It was a whisper from the past, a nearly perfect blackbody spectrum at a temperature of about 3 degrees Kelvin. The hum was the sound of the universe's birth, the signature of the Big Bang. This serendipitous discovery, an echo of the Big Bang, earned Penzias and Wilson the Nobel Prize in Physics in 1978. The accidental discovery of the CMB has since then significantly shaped our understanding of the universe and its origins, providing an important piece of the cosmological puzzle and a testament to the power of serendipity in scientific discovery. The CMB is not just an ancient cosmic whisper, it's a treasure trove of information about our universe. It's like a cosmic time machine taking us back some 13.8 billion years to the very early universe, just a few 100,000 years after the Big Bang. The CMB's existence itself provides compelling evidence for the Big Bang theory. This radiation is a relic of the hot, dense state of the early universe, when everything was packed into an incredibly small space. The fact that we can detect this radiation today supports the idea that our universe started out in this hot, dense state and has been expanding and cooling ever since. But that's not all. Detailed measurements of the CMB have allowed scientists to determine the fundamental parameters of the universe with unprecedented precision. We're talking about things like the age of the universe, its geometry, composition, and expansion rate. These are the fundamental building blocks that help us understand how the universe works and how it has evolved over billions of years. When we look closer at the CMB, we also see small temperature fluctuations, tiny variations on the order of 1 part in 100,000. These are believed to be the seeds from which the large-scale structures of galaxies and galaxy clusters formed. In essence, the CMB is like a baby picture of the universe, showing us its initial conditions and how it has grown and evolved over time. More recent observations of the polarization patterns in the CMB have provided insights into the dynamics of the early universe and may offer evidence for the existence of primordial gravitational waves. These waves are a key prediction of inflationary cosmology, a theory that explains the universe's rapid expansion just moments after the Big Bang. Finally, the existence of the CMB implies the existence of a cosmic neutrino background, a sea of relic neutrinos left over from the early universe. This is yet another piece of the cosmic puzzle that the CMB helps us uncover. The CMB, a relic of the early universe, continues to reveal secrets about our universe's past, present, and perhaps its future. The discovery of the CMB was not the end, but the beginning of a new chapter in cosmology. From this point forward, we've been able to delve deeper into the mysteries of our universe, and each new discovery has opened up a myriad of questions, keeping us on a never-ending journey of exploration and understanding. One of the most intriguing avenues of ongoing exploration is the search for B-mode polarization in the cosmic microwave background. This elusive signal is a potential fingerprint of inflation, a theory that proposes a period of rapid expansion in the early universe. Detecting this signal would be a monumental breakthrough, providing empirical evidence for inflation and potentially even shedding light on the existence of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of relativity. But the CMB isn't just a window into the early universe, it's also a potential gateway to new physics. For instance, the cosmic neutrino background, a sea of relic neutrinos left over from the early universe, is a direct implication of the existence of the CMB. Although these neutrinos have yet to be directly detected, their existence could have profound implications for our understanding of the universe, potentially revealing new physics beyond the standard model. Moreover, the CMB continues to yield a wealth of information about the fundamental parameters of our universe. By studying the minute temperature fluctuations in the CMB, scientists have been able to determine the age, geometry, composition, and expansion rate of the universe with unprecedented precision. This is an ongoing process, and with each new observation, we refine our understanding of the cosmos. As we continue to probe the CMB, we're pushing the boundaries of our knowledge, venturing into uncharted territory, and challenging our understanding of the universe. Each new discovery, each new observation brings us one step closer to unraveling the mysteries of the cosmos. As we continue to gaze at the cosmic microwave background, we are, in a sense, looking back in time, attempting to decipher the story of our universe's birth and evolution. The study of the CMB doesn't just illuminate our universe's past, it also offers a cosmic perspective on our place within it. As we unravel the mysteries of the cosmic microwave background, we're not just peeking into the cradle of the universe, but also placing ourselves within that grand cosmic narrative. This ancient light that pervades our universe isn't just a relic of the past, it's a testament to our shared cosmic heritage. Think about it. The photons of the CMB we detect today were once entwined with the very matter that makes up our bodies, our planet, our galaxy. When these photons decoupled from matter, they embarked on a journey that spans billions of years and countless light years, only to be detected by our instruments and analyzed by our curious minds. This profound connection isn't just poetic, it's scientific. The same laws of physics that governed the early universe still apply today, right here on Earth. The forces that shape the cosmos also shape the world around us and even the cells within our bodies. Our understanding of the CMB has also given us a deep sense of scale. We've learned that our planet is but a speck in a galaxy, which is itself a speck in the universe, and yet it's from this tiny vantage point that we've been able to glimpse the birth of the cosmos itself. We've also learned that the universe isn't just vast in space, but also in time. The CMB is a snapshot of a moment some 380,000 years after the Big Bang, offering us a view of the universe in its infancy, long before the formation of stars, galaxies, and planets. These revelations humble us, but they also inspire us. They remind us of our incredible capacity to explore, to discover, to understand. They remind us that through science and curiosity, we can connect with the cosmos and find our place within it. The cosmic microwave background reminds us that we are a part of this vast universe, born from the same cosmic seed, forever connected by the whispers of the Big Bang.